So this talk is about system simulation with gem5 and SystemC and also other tools. And we have only half an hour, so we cannot tell you all the details, and therefore I encourage you to look at the paper and also in /util/tlm in the README file. There you get an impression how exactly this works. So why is SystemC important? I have some slides here about virtual prototyping with SystemC. And these virtual prototypes that I used, SystemC based in industry, they are functional software models of physical hardware, and they provide controllability over the entire system and offer powerful debugging and analysis techniques. And a cool thing about all these virtual platforms is that we can reuse them for future projects. And what we can do as hardware engineers is fast design space exploration. That means we can try out different things like how big is my cache, or what is the number of cores that I should use. And it's easy to exchange. So if I build a FPGA prototyping board, then I have to send it in another country. This is more complicated. So here we have just software that we can email. And what is also important, that is for us in Fraunhofer Institute, is that we can already develop software before the actual hardware is there, and therefore we can basically make a shift left such that time to market is reduced, and at the end, hopefully also the product gets a better quality. So we have some use cases that we will show also later. On the left side, that's what's going on at TU Dresden also with NOx simulations. And on the right side, we see advanced DRAM simulations with DRAM Sys. I will show you that later. Okay, about SystemC in general. SystemC is a standard from IEEE, and it's there for modeling hardware components and software components. And it extends C++ to an event-driven simulation kernel, and it has various levels of accuracy that it offers. And it's maintained by a group called Accelera. And the idea was, of course, to have 10 up to 100 times faster cycle-accurate simulations compared to VHDL and Verilog. However, so the normal cycle-accurate SystemC is still not fast enough to boot an operating system in a reasonable time. And that's the reason why they came up with the idea of transaction-level modeling. So here we see again a cycle-accurate model, which has on all the components a clock and is pin-accurate. And we simulate on each pin the events that are happening. And then you know that you get these crazy waveforms, and you have to identify what's going wrong maybe. And on the other hand, what is TLM now offering? So instead of simulating all these bazillion events, communication gets abstracted with the help of function calls where we transfer references. And that makes the simulation, depending on the level of accuracy that you choose, up to 10,000 times faster than in VHDL simulation. So how does it work in general? So you could have a system like this with a CPU, a bus in between as interconnect, and then target memory and target I/O. And when you want to communicate now, you draw a so-called payload reference from a pool. And this is basically then a pointer to a payload object that has the information like command, address, data, and so on and so forth. And with function calls, you transfer this pointer to the target, then you do something there, and you transmit the thing back. So that's basically TLM. And you can already see that this is very similar to gem5 behavior, and we will explain that later. Okay, just to give you a brief idea what TLM is, so there are several use cases. So you can model platforms with TLM that are just for software developing or software performance analysis. So that's what you see on the left side. And then we have architecture analysis and hardware verification. This is more for the hardware guys. And therefore you have basically two coding styles. One is loosely timed, and there it's using the idea of debug transport and blocking transport. And this debug transport is basically that what you have in gem5, what you call functional, and blocking is that what you call atomic. And on the right side you have the non-blocking transport, which is very similar to the timing access in gem5. And therefore you have different mechanisms, and I don't want to go into detail about them, but it's a standard, and if you stick exactly to the definitions there, you have a full interoperability. So if you get a model from another company, you just plug it together with your model and it will work. Yeah, and therefore TLM is widely used in industry. You can see that there are a lot of tools from vendors like Synopsys, Platform Architect, for example, but also other tools from Mentor and Imperas, and also a lot of models. So for ARM example, there we have the so-called fast models, and they have only this loosely timed blocking kind of TLM modeling, and it's based on JIT, and it's non-free, and it's a library, so you cannot change these models. Then we have also the Carbon models. So Carbon is a company that was acquired recently by ARM, and what they did is that they translated their HDL models into kind of SystemC models, compiled them, and shipped them as a library. So they are cycle accurate, so very accurate, but they can also not be changed. And then you have also models from Imperas, but they are free, but only loosely timed. So somehow there was a free, very accurate model missing, and therefore we had to look on gem5. Yeah. Okay, I hand over to Christian now.
Yeah, so I'm going to show you how we can actually couple gem5 with SystemC and then build a co-simulation environment. So actually, gem5 already supported a coupling to the SystemC kernel. And I'm just going to show you quickly how that works. So when we look at gem5, then it's basically an event-driven simulation kernel, and then some logic that models hardware. And now what we can do is we can compile gem5 as a library and only use this logic. And we can link this to SystemC project. And then what we have is a SystemC simulation kernel and gem5 logic. And now what we need is something that couples these two. So this is why a module was introduced, SystemC Module gem5 sim control. And basically what it does is it replaces the gem5 event queue with a hook to the SystemC event queue. So whenever you would schedule a gem5 event, what happens is you get a SystemC event, it will be scheduled, it will be executed, driven by the gem5 logic. So this already worked a while ago. The problem with this is that there is no way of communicating. So you can hook your gem5 to the SystemC kernel, but you can't communicate to other SystemC modules. And this is why we started to work on a transaction to TLM, so that we are capable of plugging in any other SystemC model and hook it to gem5 modules. Okay, so let's have a look at transaction models in gem5. So as Matthias already mentioned, there is the timing, atomic, and functional models. And these correlate very well to the interfaces that we have in SystemC TLM. So the timing model in gem5 is very accurate. It provides a lot of timing details. And the concept is very similar to the non-blocking transport interface of TLM. Similar, the atomic model in gem5 focuses more on fast transactions and doesn't provide so much timing detail. And this correlates well to the blocking interface of TLM. And then there's the functional model, which is used for initialization, debugging, and so on. And again, there's the counterpart in TLM, which is the debug transport interface. So what we can do now is we can create a transactors. So we already have external ports in gem5, and we created external ports that connect to TLM. And then we created some transactor modules on SystemC. And what we can do is we can hook the two together and transact from gem5 to TLM and vice versa by simply translating these interfaces, these SystemC interfaces, to the gem5 models and vice versa. Okay, so let's have a look at an example how this works. So we have a very simple system here. We have a CPU simulated in the gem5 world. Then we have our transactor, and we connect this to a memory simulated in the SystemC world. If you want to send a request now to the memory, what the CPU does is it will create a gem5 packet, which has some metadata, like a command, data, some data array, an address, and the size. And then it will forward this reference to the external slave. Now what happens is we need to translate this gem5 request, the packet, to the SystemC generic payload. So what we do is we create a new generic payload object, and then we copy all the metadata from the gem5 packet to the TLM payload. Fortunately, the metadata is very similar, so we can actually just copy it. And now we need to keep track of the original packet that we generated this payload from. So what we do is we hook this reference to the packet as an extension to the generic payload. And now we follow the TLM procedure, forward the payload object to the memory. The memory will answer the request. So if it's a read request, it will fill in the data and create a reply. Then eventually the request, the reference returns to the slave transactor. And now what we can do is we can restore our original gem5 packet by removing the extension from the generic payload. Now we can update this packet with the metadata from the generic payload so that we have all the information that the memory filled in into this payload. And now we can again, we can destroy the generic payload, and then we can simply follow the gem5 procedure and return this reference as a response to the CPU. And this is basically how it works. It works similarly for the other way around. So when we want to communicate from SystemC to gem5, then we create a gem5 packet, and we hook the original generic payload as a sender state to the gem5 packet. Okay, so how can you use it? So first of all, I recommend you to have a look at the examples that we created, and you can find them in the utils TLM directory of gem5. So there's the example which I just showed you, gem5 CPU connected to SystemC memory. And we also have an example for the other way around, where we have a master and SystemC connected to a memory in gem5. There's also an example that uses elastic traces. And we also have a full system example which boots an operating system in a system where the memory is simulated in SystemC. Yeah, just quickly about the general flow of when you want to use on the binding. So what you need to do is you will need to compile gem5 normally, and you will also need to create a library of gem5. And then you need to create a SystemC project which uses your SystemC modules as you like, and that also instantiates some of your of the gem5 modules, like the transactors and the sim control. Then you simply compile your project, and you need to link it against the gem5 library. And then the last thing that you need is a configuration for gem5. And for that, you simply run gem5 normally, providing some Python script. And what you get then is an config.ini file. And this config.ini file, so you need to hand to the gem5 sim control, and then this object will be able to create all the gem5 objects and will instantiate the gem5 subsystem and start your simulation. So I have some more detailed view here for the slide example. So just quickly to show how a memory could look in SystemC. Yeah, I think it's not too interesting for now. Basically, what you do is you define some socket for the communication. You need some storage. You have a constructor written in a special way, following the SystemC standard. And then you also need to define your TLM interface that implement the communication. And apart from your actual memory, you also will need to define your top level in the SystemC world. So this is the SystemC main, which instantiates some SystemC modules. So what we need is the gem5 sim control module. We also instantiate a transactor and then the memory. Then we bind them together, so we perform all the connections, and then we simply start the simulation. That's all we need to do. Yes, so there is some stuff hidden in these config nodes. So what is also very important is that you need to pass the config.ini file, so the path to this file, somewhere to the sim control module. Then we also need the other part. We need to configure gem5. So this is from the TLM example, the Python script. And again, it's a very simple script that just creates a system. It creates a traffic generator CPU. It creates a crossbar bus, connects them. And it also creates an external slave and connects it to the bus. And then, again, it starts the simulation. OK, and so how to run this? First, we need to build the project. For this example, it's quite simple. There's a sconce script for that, so we simply need to run sconce. Then we need to generate the configuration file. For that, we run the normal gem5 with our Python script, and we'll get a configuration file. And then we run our project, our binary that we generated from the SystemC code, passing the configuration file that we just generated. And now the gem5 sim control will build the gem5 system, instantiate all the objects, and we'll see that they are connected to the right transactor. And then we get an output like this. So this shows that the simulation actually runs. So we can pass a debug flag to the gem5, and then we see the output. It generates requests, and it receives responses. OK. So what do we use this for? So I myself, I work in the orchestration path of the CFAD, Center for Advancing Electronics Dresden. And we are working on a programming stack for widely heterogeneous systems. Yeah, so we try to combine data flow models, data flow compilers, adaptive runtime systems, an operating system, and also model checking into one stack in order to easily deploy software to wide heterogeneous systems. And for that, we need some platforms to try our technologies on. Of course, there's real hardware, but we also need some flexible simulation platforms. And when I started to work on this, we had to decide whether go for gem5 or go for SystemC. I was very fond of gem5 at this point, but there were also strong points for SystemC, and in the end, I decided to do both and worked on this connection between SystemC and gem5. So a system that we can simulate looks something like that. So we have a network on chip, we have several tiles, and one of those tiles could be modeled in gem5. So we have a subsystem consisting of CPU, some local memory, bus, a data transfer unit, all simulated in gem5, and then we connect this to SystemC, and we can simply plug this to our SystemC NOC model. And we can even plug this into a Synopsys platform architect. So this is the system as I just showed you, and a tile then can look like such that we have our master and slave transactors. We connect this to the sim control. And then there's a fourth module, which is simply a bridge that translates the standard TLM requests to our NOC protocol. And then, of course, we can also use the trace analyzer. We can see what's happening in the system. So here we see a boot of an operating system. So P0 wants a kernel, and then it loads the binaries to the workers. And of course, you can also zoom into that and look at all the details of your TLM transactions. Okay, so that's for my use cases, and I'm going to hand back to Matthias. So he's going to explain his.
Thank you. Yeah, so when I did my PhD at University of Kaiserslautern, I worked a lot with DRAMs, and especially with 3D stacked DRAMs. So here you see an example simulation of wide I/O DRAM, where we have modeled the cores with gem5, and we run an Android with a benchmark on it, and you can see how these cores really heat up the memory stack on top of it, and there we did a lot of research. And we do that with the DRAM sys tool. It's written in SystemC. And the tool includes a DRAM power model, a thermal model, and also a retention error model, because we worked also on approximate DRAM techniques. And as you can see, for example, when you boot Linux, then this slows down the gem5 simulation by almost 2x. And mainly the reason is because the DRAM model is much more detailed as the DRAM model in the gem5. And therefore we could see that this coupling has a very small overhead. So what you can do with DRAM sys, I think you saw it already in that video, but there are also some other tools like a trace analyzer which visualize the TLM transactions that are going on in the system. So here this is, for example, a DDR4 memory where you see they have 16 banks, and also you go into power down modes. These are the gray bars, and you can really analyze what's going on in the system. And this trace analyzer has also another tool which checks for JEDEC compliance. That's always cool when you implement a new memory controller architecture, that you can check that you are still compliant to the memory standards. And there are also some other tools that can generate some performance statistics for you and graphs. So that's where we use this gem5 connection to SystemC very, very often. And now at my new position at Fraunhofer, we do some other stuff. We do software development and software architecture mainly for embedded systems. And also there we use gem5 in order to simulate embedded systems. And we are not coupling it this time to SystemC. So we couple it with a Java-based simulator, but we use a lot of the techniques that we have developed for SystemC in order to get this happen. So we have a tool there which is called Feral. And this tool is basically a simulation coupling framework. So we can connect gem5 now to several other models. This can be SystemC, but can also be a CAN bus simulator or Simulink model from MATLAB. And with this kind of platform, we do a lot of development, especially software testing. So what we do with it is basically for normal software testing, you very often instrument the binary, which is very intrusive, and you can change the behavior of your program. And in this project, we instrument gem5 instead. And we keep the binary as it is. So it's really the binary that's shipped to the customer. And that's what we do here. And we reuse techniques from the SystemC coupling. Okay, so to summarize, so we have now the full interoperability between gem5 and SystemC. And we are fully compliant to the SystemC standard, and it's part of the repository. So there are some possible next steps. So some people talked to me already if it would be possible to maybe change the simulation kernel of gem5 completely to SystemC and replace everything and also the connections to TLM. I think this might be possible, but it's not something that we can just do over the weekend or so. And I think another important question is, can we maybe remove the step for this config ini file generation and directly run that with the Python configuration? And of course, we are open if you have some other suggestions. Okay, thank you very much.